In the same manner that we consider some joints as pinned and others as rigid, based on their relative stiffness, we also idealize loads to use in our analysis. When loads are applied over a small area, we consider them as point loads. When they're distributed over large areas, we consider them as distributed loads. Let's look closer at how we can designate and work with loads.
When the dual wheels of a truck are on a bridge, there is a definite contact area where the wheel load goes into the bridge. AASHTO defines the standard contact area for dual wheels as 20 inches wide by 10 inches long. The truck wheels are still generally assumed to be point loads. Car wheels, special truck wheels, unique oversized vehicle wheels, and wheels on heavy construction vehicles are all taken as applying point loads. As a rule of thumb, loads that are added and applied over small lengths compared to the member size are usually assumed to be point loads. Many loads, like loads on the floor of a building, are applied to the floor over a large area. The floor weight itself from the concrete floor is uniform over the whole floor area. Now let's look at how floor loads in this building are applied and then collected by the structures. We start by looking at how the structure works. The floors consist of precast hollow core panels. Each panel is a separate 6-foot wide piece. The panel sits on a steel beam at each end, so they are simply supported. Note that some floors only have beams at the hollow core ends. Others also have beams along the sides. The beams are attached to columns with rigid joints. This is a braced frame combined with a moment-resisting frame. The joints at the brace ends actually are partially rigid, but for analysis we assume that they are pinned. The column has a splice with a rigid connection. A single full-length column would be too long to ship on a truck, so 2 separate lengths are spliced together in the building. Now let's do an examination of the floor loads. The dimension for one bay of the frame are 14 feet wide, perpendicular to the span of the hollow core, and 16 feet long between beams that support the hollow core.
First, we estimate the loads of the floor. The floor is a 6-inch thick hollow core precast concrete panel, weighing 66 pounds per square foot. Finishes, such as floor tile on the floor and finishes on the ceiling below, will add another 4 pounds per square foot. If the room is full of people or furniture, we could expect another 40 pounds per square foot. Then the total floor load is the sum, or 110 pounds per square foot. With the floor load known, now we can see how much of the load goes to the beams. We're going to look at the floor where the hollow core is only supported at the ends. We take one bay of the floor out, with each corner a location of a column in the frame. This bay is 16 feet long and 14 feet wide. Then we look at a 1 foot wide strip that runs from one supporting beam to the other. Each beam will carry the weight of 1/2 of this strip, so we can draw a dividing line halfway across the span. Then we want to figure out how much load is on this strip. So for every 1 foot length of the beam, the floor area carried by the beam is going to be 1 foot by 8 foot, or a total of 8 square feet. The load on this 8 square feet of floor is just 8 foot squared times the floor load, 110 pounds per foot squared, or 880 pounds. So for every foot length of the beam, the floor transfers 880 pounds. Then the beam loading from the slab is just 880 pounds per foot of length of the beam. We know how much load is coming from the floor onto the beam per foot of length, but what is the total load on the beam? Take the load per foot times the beam length for a total of 12,320 pounds. There's an alternate approach for finding the total beam load. Again, we start by taking our 14 by 16 foot bay with a beam at two ends and divide the 16 foot span in half. Then we look at the shaded area. Half the total slab area is carried on each beam. That area is going to be 14 feet by 8 feet, or 112 square feet. This is called the tributary area. The total load on the beam can then be calculated from this area. It'll be 112 square feet times the floor load, 110 pounds per square foot, or 12,320 pounds. This is the same load we found before. Therefore, we can use the tributary area method to quickly find the load on a member. Let's look at a different floor, the same size as the one previously examined. This is now a solid cast-in-place slab, not the precast hollow core. The dimensions are the same, but the slab is supported by beams on all sides. Now the question is, how much of the floor load goes to each beam? We'll again use tributary areas. To do this, let's look at a plan view of the slab. Start by drawing 45-degree lines from each corner toward the middle until you intersect another 45-degree line. Then look at the individual pieces of the floor area. The floor along the side with the 16-foot beam is shaded. Load from this area will go to that beam. To determine the size of the load, let's first dimension the shaded area. If we go to the middle of the beam and look at a 1 foot wide strip near the middle, we can calculate the load on that strip as 110 pounds per square foot times 7 square feet, or 770 pounds. So we have 770 pounds per foot of length on the beam near its midpoint. Obviously, near the end of the beam, the load will decrease to 0. The actual loading on the beam then looks like this. There's a constant load of 770 pounds per foot on the middle 2 feet. And then goes to 0 at the end of the beam. Looking at that loading again, and if we define x as a distance from the left end of the beam, the load varies linearly. So for x greater than 0 but less than 7 feet, the load at any point would be 770 pounds per foot times x over 7 feet. We can do an identical investigation on the beam along the 14-foot edge of the floor. Looking at the plan view again and drawing the 45-degree lines, we see the tributary area now is triangular. At the midpoint of the triangle, the load again reaches 770 pounds per square foot. And it's 0 at the end of the beam. That creates a triangular beam loading that varies linearly. For a distance x greater than 0 but less than 7 feet, the load at x is 770 pounds per foot times x over 7 feet. Now we can also use the tributary area method to estimate forces in columns. A sketch of the same building frame with 14-foot by 16-foot bays is shown. We want to estimate the amount of floor load going into columns A and B in the plan view. Drawing the plan view helps in seeing the tributary areas. Then we draw a dashed line at 1/2 the span length away from each column. For column A, we see a shaded area that's 8 foot by 7 foot. Drawing the dashed lines at half the span away from length from column B, again we have a shaded area that can be assumed to contribute to the column loading. In this column, the tributary area is a total of 14 feet on one side and 16 feet on the second. Calculate the load on column A first. The tributary floor area is 8 foot by 7 foot or 56 square foot. The load is 56 square foot times 110 pounds per square foot or 6160 pounds. In column B, the floor tributary is 14 by 16 foot or 224 square feet. The column load is 224 square feet times 110 pounds per square foot, or 26,640 pounds. So these forces can simply be taken as load per square foot times tributary area.
Let me quickly summarize what we've seen here. There really are no loads applied at a point. Any real application of load occurs over some area, which may still be very small. When the load is applied over a small area or length, compared to the member size, we often consider it as a point load. Truck tires are assumed as point loads on bridges because their contact length is 10 inches. Compared to a bridge length of 70 feet, that 10 inches is only 1% of the span length. Very small. When we have loads applied over large areas, like a uniform load when a floor is filled with people, we can use a rule of thumb to estimate where those loads go or what they do. The first rule of thumb is for floors on beams. If a floor slab is supported by beams on only 2 sides, then take a 1 foot wide strip stretching from one support beam to the other. Calculate the area of the strip. Half the strip area is resisted by each beam. Calculate the beam loading as the floor load times the area of half the strip. A second rule. If floor slabs are supported by beams on all sides, then draw lines at 45-degree angles from the end of each beam. Where these lines intersect, connect the intersections. The resulting areas adjacent to each beam are carried by the beam. Calculate the beam loading as the floor load times the area. The third rule of thumb is for columns. For the load going to a column, draw lines 1/2 the span length away from the column on all sides of the column. The resulting areas adjacent to the column are carried by that column. Calculate the column load as the floor load times the area.